Okay, so we are discussing about this Prim's algorithms. Prim's algorithms for finding this minimum cost spanning tree. Okay. That we were discussing. Okay. And here as we have seen that here the main idea is okay, just like the shortest path we are having. Whenever I am discovering this node or this node here, then all the adjacent vertices we are, in some sense, we are relaxing. Okay. That means through this, whether I can reach here with less cost that was previously computed rather than previously computed cost. Okay. And now, as we move on from here on, say, if the next guy is this vertex, then from here, whenever I see that, okay, which are the edges, okay, so I'm taking all the calculation. That means all the adjacent vertices from here. I am updating the cost, and then I'm taking out of all these which are the edges which are less costly. Okay, and then we are taking the decision. That means which which edge to be selected next. Okay, so like this way, this or which vertex will be selected next, and in this way we are proceeding. Okay, so that we have seen in the last class, and now what we got to do is we have to check its optimality. Its optimality. Okay, so here. So this Q, we are having this source vertex key that will be assigned as 0. Okay, so here this is the source vertex. Okay, but we have already discussed this, but still this is the queue we are maintaining with all these vertices. So all these vertices will be having cost infinite cost, and the source vertex will be having 0 cost. Okay, so the top of the queue, that means front of the queue will be having this source vertex. So source vertex we have to extract here, extract mean, and then all the vertices adjacent to this u, okay, we have to check this condition. Okay. We have to check this condition. That means the weight of uv, this edge, is more than the earlier computed value of this vertex v. Okay. So if I take this guy initially was infinity. Now once I'm taking this edge, okay, uv, wuv, then I'm saying that wuv is less than the key value of this. So this vertex will be updated with this cost 4. Okay. And this guy will be updated with, I guess, with cost 8. So this is 8. So this is 8. And this is 4. Okay. Right. And we are maintaining one Q, and in that Q value, okay, so this B node will be at the front of the queue. We are maintaining priority queue, then 8, and then other nodes will be coming. Okay. and we have to extract in the next iteration this 4, okay, this 4, and then we have to move on with this. Okay. So once I am discovering this, okay, so now this guy is 8, so its value previously it was infinity, now it will be updated with 8, or yes, 8. So this is the age 8, the cost is 8, okay. And now the value of this, if I am taking this age, then previously it was 8. Okay. Previously it was 8. Now I am seeing that through B I am reaching with cost 11. So it will not be updated. Okay. And all other cost will be infinity. Right. So this is 8 and this is 8. So we have to break ties, say lexicographically. Okay. Or say whichever letter is, that means whichever letter may be coming first or coming next. Maybe I can take this guy T and this is H, so T might be the first one. You can take H as the first one also. Okay. So if I am taking C, then that H will be included in that set, okay, that tree, and then we are having, as we promised, that when the Prim's algorithm will be going on, so you see there is no disjoint way of growing the tree. Okay, so this was our root node, and then this was connected, and then this is connected. Okay, so in the Kruskal algorithm we had some structure here and then some structure growing here, and then say we are joining this structure. Okay, but here from the very beginning the tree is growing. Okay, so that is the way, and I told you that, okay, always we have to check V belongs to Q. So this checking is V belongs to Q. Okay, so this checking will be helpful to check that, okay, we are not forming any kind of cycle. Okay, so this is the way the Prim's algorithm is going on. You can fill up, you can check the way they are proceeding. Okay, so this guy is there, and then this guy, I guess this will be, I will be having 2 value 2. Okay, so I will be 2, so I will be selected. So as this you see, this I is selected. Out of all these nodes, this guy is the minimum. Okay, right? And then this C also, whenever I have discovered this C, so this guy, if it is having 4, so F value will be 4. So next, so I guess this guy was there, H with 8. I already selected, so F, I guess, and then D is also there. Okay. So D with 7, H with 8, and F with 4. Okay. So next guy that will be selected is F. Okay, so this F is selected, right? And once this F is selected, so its adjacent edges to be updated. Okay, so it will be updated with 2. G will be updated with 2, and then this guy will be updated with 10. Okay, so this is the 10. Okay, right. And now you see this the next guy, this F I have selected, and then this G is selected. Okay, so G is selected. So this is, you see, this is the way it is growing. Okay. The tree is growing like this. From the very beginning, you see no disjoint way we are creating this. Okay, right.
So,
Yes.
sir, the node G is selected through F or it is selected through H because H weight between G and H is 1.
Oh, no, no. It is this H is not selected yet. Okay. So this H, once it is not selected, then how can it be updated? Okay. So that value before F was discovered, that value was infinity. Are you getting?
Yes, sir.
Hmm. So that value
Yes,
was
sir.
infinite, and so that's why G, after I am discovering this F, then G will be updated. Okay. So like this way it's growing. You fill up the other part of the tree. So this is the Prim's algorithms, and uh, you see what we are doing is we are always some vertices which are Q inside Q. One of the vertices which is having the minimum value, that I am adding up in the tree. Okay. So this observation will be helping us to get its. We are getting the lightweight vertex, right? So that vertex we are taking inside in taking into the minimum spanning tree. Okay, in this set we are taking. Okay, so that will be helping us. And you see, every time we are extracting one such vertex. Okay, so at some point of time Q will be exhausted, right? And we are including the guy which is having the minimum height. Okay. Maybe so this loop invariant, this is called the we can prove this the optimality of Prim's algorithm with this loop invariant technique. Okay, so the loop invariant technique is used in CLRS many a times. Okay, so it is first it is using in insertion sort. So in insertion sort, what we are having, we are incrementally sorting the array. First we are taking say 2-element array, and then the next guy is included third element, and then including that third element everything will be sorted. I don't know yet the status of the other elements which are present in the array. Okay. So the next 4-element array we will be considering, the fourth one. And whenever I am considering the fourth one, already all the elements comprising of these 3 elements are sorted. And the fourth element is placed in this sorted list of 1 to 4. Okay. So before some iteration we have got a sorted one. And then after the iteration we are maintaining that sorted one, that sortedness. Okay. So that is the idea of loop invariant. Prior to any loop, something is of our desired nature. That means in insertion sort, what we are targeting that at the end of the loop, all elements will be in sorted order. Okay, so we are incrementally doing that thing. 2 element array sorted, then 3 element array sorted, okay, then the 4 element array sorted. Like this way we are proceeding. And the fourth element whenever I am taking, or fifth element whenever I am taking, okay, so fifth element whenever I am taking, all the 4 element array before going to the next loop, all the fourth element array are already sorted, and we are maintaining that considering the fifth element. So that means whenever I'll be ending the loop, all the elements consisting of 5 elements will be in sorted order. So this is the same way, same technique is used in algorithms after algorithms in CLRs to find out that whatever desired result, okay, here in insertion sort, the desired result was that, okay, we have to have this sorted order. And this loop invariant technique we will be using here in this Prim's algorithm, okay, to get its optimality, right? So what we are maintaining here is prior to each iteration of the while loop, okay, prior to each iteration of the while loop of line 6 and 11, okay. So that that thing, I guess maybe we can take it here, okay. So which one? So I guess this one, this one. So just let me check whether this can be copied or not. Okay, so we have got this Prim's algorithm right here. Here, this is the Prim's algorithm, right? Okay. So prior to each iteration of the while loop of line 6 to 11. So this is the loop, as we are calling that. This is the loop invariant technique. Try to understand. This is the loop invariant technique. In the insertion sort, we have to maintain some while loop, okay, right, or some for loop, right. So before going to the for loop, some structure of the array is maintaining, say 3 elements array already sorted. Then whenever I am going to the next iteration of the loop, I am taking the fourth element. And inside the loop, I do whatever processing need to be done. Okay. So here, prior to each iteration of the while loop of line 6 to 11, because this while loop is doing the bulk of the work, okay, is doing the bulk of the work or the major work which is necessary for this spanning tree formation. Okay, minimum spanning tree formation. Now, prior to each iteration of the while loop, we are maintaining a set A, okay, consisting of vertices and its parent pointer. So parent pointer you may ignore right now. So consisting of vertices, and that vertices will be from this set V belongs to, say, I am taking the loop invariant V minus the Q. It will be better understandable. So the V, that set V will be coming from this V minus Q. Okay. That means we are having this V means all the vertices and Q means whatever vertices remaining in the Q. Okay. Initially, whenever we have the first time we are going, at that time you see this the set will be consisting of no elements. Okay, the no elements will be consisting of, because this so this A will not be consisting of any elements, because V, how many vertices we are having? Say we are having 4 vertices in the, this is the graph. So 4 vertices I am having, and Q will also be having 4 vertices. So V minus Q will be 0. So we call that prior to the first iteration it is vacuously true. That means nothing is done. Okay. And we have to understand this thing, that the vertices already placed into the minimum spanning tree will be from this V minus Q. Okay. So when the while loop will be under operation, we have seen that, okay, we are extracting some node from this Q, and we are putting it into this set A, right? So the vertices already placed into the minimum spanning tree will be from V minus Q. Okay. Say for after the first iteration, when the second iteration begins, then we can see that what could be the structure of the vertices which are placed in the minimum spanning tree. So by this loop, the vertices which is having the mean cost, that will be extracted, and that is put into this. The vertices already placed will be from V minus Q. Okay. So after ending this loop, after the first iteration, can you tell me, say if this is the structure Q, so we had 1, 2, 3, 4, 3, 4, 7. So Q, maybe we had 1, 2, 4, 3 or 3, 4. 1, 2, 3, 4, say this is the source node. After the first iteration, this will be extracted. Okay. So what will be the structure of Q? Maybe 3, 2, 4, something like this. How many vertices we are having? 3. So after the first iteration, when the second iteration will be beginning, prior to that, the vertices already that will be placed in the minimum spanning tree will be from V minus the Q. V is having 4 number of vertices. Okay, that means 1, 2, 3, 4, and Q will be having 3 vertices left. So V minus Q will be having 1 vertex that is placed in this set A. Okay. So this is prior to the second iteration. Okay. Prior to the second iteration, we can say that this structure is maintaining. We are maintaining this structure. And then what the third thing, third one is checking that for all the vertices, V belongs to this Q. All those vertices which are there in this Q, okay. If V dot pi not equals to nil, that means already these are relaxed. Okay, V dot pi not equals to nil. Then V dot pi is less than infinity, then definitely that is once this root node is discovered, okay, so its adjacent nodes will be having this V dot pi will be nil because it's relaxed via this and it's relaxed via this. Okay. So V dot pi will be nil, and then initially this node was infinity, but once I am going through here to here, then definitely this V dot key value of this node will be less than infinity. Okay. Some value will be there. And V dot key is the weight of a lightweight edge, V comma V dot pi, connecting V to some vertex already placed into the minimum spanning tree. So whenever means this V dot key, so which vertex I am taking into consideration, that means the lightweight one, and then its corresponding edge, say this guy is the lightweight one, its corresponding edge will be connecting some vertex already in this minimum spanning tree set. Okay. So U is already there in this set A minimum spanning tree, and then the corresponding lightweight edges, we are considering this vertex. Lightweight vertex means we are considering this edge, because of this edge, say 2, it has got 2, right? So this lightweight edge corresponding to this, okay. So that means this V is this this guy, and V dot pi is this U. Okay, its parent pointer is pointing here, V dot pi. Okay, and we are taking this into the minimum spanning tree set, means we are connecting this edge. Okay, so that means this is the so far minimum spanning tree. Okay, right. So what exactly I am doing here? You see, so we have got this, say another iteration, and we have got here, we had these two, say in the tree structure, we had these two nodes. By this condition, we are having some kind of optimality here. Okay. So far we have got just a minute. So far we have got this minimum spanning tree, and then out of these two, say this guy is 3 and this guy is 5. So in the next iteration, so this is prior to the next iteration, we have got one spanning tree is this. Okay. Now what I am doing in the next iteration through this loop, I am taking, say, this one is the lightweight edge corresponding to this vertex, lightweight vertex. So I'll be taking this edge into the tree, instead of this. So you see, by this condition, what we are doing, whatever was not there, out of this, the minimum one, so far this was the minimum. And then out of this, whatever was minimum, that I am adding through this condition. Okay. Then when this loop ends, what I am getting? Prior to the next loop, next iteration, I am getting one minimum spanning tree. Okay. One minimum spanning tree. Okay. So at the end, every node will be considered like this way, and then we'll be having one, say, the next node that may be included. Once this guy is included, maybe it is 4. So 4 and 5, instead of the 5 and 4 will be there in the queue, so 4 will be selected. So like this way, the next minimum will be added to the tree. So you see, incrementally, so initially we had 2-node structure, then I am having the 3-node structure, then I am having the 4-node structure, and with this loop invariant I am maintaining the minimum spanning tree property. Okay. So once all the nodes will be exhausted, then definitely we will be having the minimum spanning tree consisting of all the vertices. Okay. So this is the loop invariant proof of the optimality of Prim's algorithms. Okay. Do you have any class after this? Do you have any class? Okay. Avijit Kumar Sinha. Avijit Kumar Sinha, are you listening?
Yes, sir.
So, how we are proving the optimality of Prim's algorithms?
Actually, sir, there was a internet issue.
Internet issue. You'll be getting 5 marks less in your CA. Noren, you note it down. Internet issue.
Sir, noted. Noted, sir.
Nobody is listening. Aditya Singh.
Yes, sir.
How did I prove the optimality of Prim's algorithms?
So we proved it by, sir, because at every step, sir, we are using a greedy algorithm. Sir, we are selecting the one with the minimum weight. Sir, that is how we are optimizing it. And sir, the time complexity will be v square, and and the space complexity will be O of v. So, sir, then that is how we can say that it is optimal. So because
did I say like that? Did I say like that? Are you listening?
Yes, sir.
What I have told? With what technique
Yes,
I proved it? What is that technique called?
Sir, Q.
Q. Ayush Anand. Ayush.
Yes, sir. Yes, sir.
What technique I called? What technique I used?
Sir, you used loop invariant technique, sir.
Have you heard, Aditya?
Yes, sir. Loop invariant technique.
Were you there in the class or you were doing something
Yes,
else?
sir, I'm in the class. Yes, sir, I'm in the class, sir.
Then I told you again and again this loop invariant technique is the most important technique in CLRS. Are you not listening at all?
Yes, sir, I'm listening. Sorry, sir.
many times should I say? Okay, Naren, তোমার mute করো. Aditya, what is your roll number?
Sir, 49.
49. Ayush?
Sir, 109.
109. And Avijit, what is your roll number? Avijit?
Hello.
Avijit, what is your roll number?
Hello. Hello.
Your roll number?
Hello.
Your roll number is what?
Sir, 186.
You know, we are having your roll number, your name, everything written, so you cannot escape like that. Naren, roll number কত?
Sir, 186.
186. Okay, you note it down.
Okay, sir.
Okay, and this, the time complexity, whenever we will be discussing any algorithm, okay, we are taking its time complexity. So here this is given as an exercise that this could be the time complexity of these Prim's algorithms. Okay. The total time for Prim's algorithm is this, and V is in the range of E, so we can say it is E log V. Okay. So this you elaborate. Okay. So this part you study yourself. Okay. Right. And you try to. So this is given as an exercise. Find out the time complexity of Prim's algorithms. Okay. So you have got Kruskal algorithm. Also, you try to analyze the time complexity of Kruskal algorithm. Right. Perhaps whenever we took this DFS, perhaps we didn't discuss the algorithm like this, how it is working. Perhaps we discussed the application of DFS. Okay. We discussed this. We discussed this bluff fill or flat fill. And this is actually the DFS algorithm. Maybe we can take a quick look on this, how it is being implemented. Okay. So in most, say, if you are going through videos in the internet, okay, many videos will not be teaching like the CLRS way, but in the CLRS way, if we take some kind of information along our proceeding, then we can do something more. Okay. So that we'll be seeing that one of the applications of this DFS is called topological sort. Topological sort, that is given as an exercise to understand, but we'll be trying to understand with this technique the connected components of a graph. So that we'll try to understand with this technique, DFS technique. Okay. So here this this is our node. This is our graph. So this is our graph. Okay. Right. So this is U. This is V. This is W. This is X. This is Y. And this is Z. So this graph is there. Okay. And now for this DFS, what we are doing. So what we are doing, we are making every vertex white first. Okay. And every vertex parent pointer will be nil. And then we are initializing one variable called time. The time when it is getting explode first. Okay. And then we are calling this DFS visit, this G of U. Okay. So this for each vertex. So you see this for each vertex U belongs to GV. If U dot color is white, we are calling DFS visit GU. Okay. So this is this thing is ensuring that every part of this graph. So we are having this graph, this portion of the graph. There we can say some kind of reachability is there. Okay. But you see from here, so this guy is connected with this. We can reach from here to here. We can reach from here to here, but can I reach from here to here? No. Can I reach from here to here? No. Okay. We can reach from this side to this side, but we cannot reach from this side to that side. Okay. So this condition is rescuing that once we have explored the component of this component we have explored, then other guys which are still white, that will be explored next. Okay, we will be coming back here, and then what are the which vertex is not colored yet, which vertex is colored white, that means which are not explored yet, that will be explored. Okay. But the BFS, in BFS, we might not be able to do this as far as the implementation is concerned. Okay. As far as the whatever implementation we have taken in our example or the CLRs, we are not being able to explore that part of this graph. Okay. In BFS. Okay. So now you see this, we'll be having, so initially everything will be remaining white. Okay, everything will be remaining white. And then we have to call this DFS visit recursively with this graph G and then this starting vertex U. So this is the starting vertex. And you see whenever it is calling this function DFS visit, so time is incremented by 1. So time was initially 0, and at the time when this U is explored first, so its value is written as 1. So this is U. If I zoom in, so this is U, and this is having two parts. One is the initial time, when it is the first time it is explored. So this is explored first time. Its time is 1 given. Okay. Time is 1, right? And then what we got to do is U dot color will be gray. So at the 3 stage, we will be coloring this U as a permanent black. So first it is white, then it will be gray, and as it is depth first, so we will be moving on, and whenever we'll be coming back here, then we can take other path, then other path exhausted, we'll be coming back here, then if no other way we can reach from here, then it will be blackened. Okay. So that is the 3-stage coloring of a node here. Okay. So now we can, for each V adjacent to this U, for each V adjacent to this U, okay, what we got to do, say we are going in this direction, say first. So V will be having this, we are exploring this V first. Okay. So once we are doing this, so if V dot color is white, then we can do this. And then V dot pi will be U. Okay. So its parent pointer, so its parent pointer will be like this. Okay. Its parent pointer. And then this DFS visit, we have to start from this DFS visit GV. Okay. So this is ensuring that in the breadth first search, we are exploring these nodes altogether first. This node, all the adjacent edges. But here, what I am doing, I am say taking this guy first, and then from here I am starting again. Not I am exploring this for the time being. I'll be doing here. Say I am going here. Then from here I have to start, and I am going there. So like this way, we are going deeper and deeper. So that's why it is depth first search. Okay.
Sir,
Yes.
sir, why are we setting v dot pi equal to u?
So I am coming from this V. I am coming V from where? From U. Okay. So that's
Yes,
why.
sir. Yes, sir.
That's why.
Okay, sir. Okay.
Who is asking the question?
Sir, I Aditya.
Aditya.
Yes, sir.
This time you are trying to understand. That's good. Okay, so V2U will be having a parent pointer, and you see this once I am calling this DFS visit again. So what it will be doing, it will be incrementing time. So this U will be replaced with this V. Okay, so this guy. And the time will be incremented by time plus 1, and U dot D will be time. Okay. So this guy V will be having its initial timing whenever it is explored. That means the next iteration, the first iteration, this guy was explored. In the next iteration, this guy is getting explored. Okay. So this is the way we are exploring this. Okay. Now what we got to do, we have to start from here. Okay. We have to start from here, and you see then we are exploring, say, this guy. We are exploring, say, this guy, and its value is incremented to 3. Okay. And then we are exploring, say, from here I have to start, as I gave you the example here. I am deeper and deeper searching. Okay. So from here I started, then I am going here, then I am going here. Each time it is explored, so it's 3. And then I am going here. So can you tell me what will be the initial time of this guy, this node? Can anybody tell? What will be the initial time of this node? So first it was 1 here, and then I am going here to here, that is 2. then I am going here to here, so it will be 3, and then I am going here to here. So that means with this
So,
x, I am going here right now. So can you tell me what will be the initial time?
sir, O of n.
Time means this time. This is, you see this 1,
Time
2,
variable.
3, that is the time I am telling, not time complexity. What is the initial time? You see here I am, here this time is not associated with time complexity. This is the time in which iteration it is getting explored, so to say. What will be the time here? Nobody is being able to say. So this is our graph we are having. This is our graph, say, and this is our graph. Say this is our graph, okay? And this is our u. This is our v. This is say x. This is y. Now, if I start exploring with the help of this DFS technique, then what will be happening? So first, this is the start node, say. This can be, you can make, this can be the start node. Say we are taking this node as the start node. Then this node having two components. One is the initial time when it is getting explored. The first time it is getting explored, so it is 1. So it is 1. I don't know its finish time. Okay, we are going here to here. And then this is the next node which is explored, so it will be 2. Then as it is depth first, from here I have to start all over again. Okay, I have to call this guy, this DFS function recursively. And then this guy is explored, so it will be 3. And then this guy will be explored, this will be 4. Okay. Right. And now you see from 4 I cannot go anywhere. Okay. Right. So I cannot go anywhere. So at that time, what it will be, so no adjacent edges, no adjacent vertex of this. Okay. That means no adjacent edges of this, right? So it is finished explode. Okay. It is finished explode, so it will be blackened, right? And then you see what is the time. So this 4, and then we have to increment the time once more, and then it is 5. Okay. So it's finished
Sir,
time. So each node, so this node is right now having this structure. Initially it was 4, and then it is finished at the time 5. Okay. Then I
sir,
have to go back here, and I have to check whether this guy having any other adjacent vertices left. Okay. But I am seeing that no vertex, no adjacent vertices left. So it will be 6. Incremented time will be incremented once. And then I have to go back here. So the time will be incremented here again by 7. Then I have to go back here. And you see here, first I explode this guy. But still one guy is left to explode, one edge. But I can reach with this edge with this vertex, but that vertex is not wide, so we cannot explore this u anymore. We have explored this through this. So the parent pointer will be like this. Okay, parent pointer also we have to have. So it's the last finishing time is 7, so its finish time will be 8.
Sir,
So yes.
sir, why are we incrementing the time after we have explored X?
Huh?
Sir, why are we incrementing the time once again after we have already explored X, sir? So because we have explored all the nodes, then after reaching X, then why are we incrementing the time again, sir? You said that after reaching X, it is time 4, and then we are incrementing it once again, so it becomes the finish time becomes 5. So why are we incrementing from 4 to 5 when we have already reached X?
No, every node in this case, every node. Okay. So if you are taking the implementation of this, okay, if you are taking the implementation from right from the word go, then you will be telling that okay, after this, okay, then again we are moving here, and then we are you see this you see this okay, see, you see this part I have discussed this part I have discussed up till this. Okay, u dot color is black, but
Yes, sir.
whenever every node is finished up, right?
Yes,
Every
sir.
node is finished up, that means it's blackened. It will be executing these two statements also, right?
Oh,
So
yes, sir.
time will
Yes,
be
sir.
equals to time plus 1. That means
Yes, sir.
4 equal to 4 plus 1 will be equal to 5, and then u dot f, its finish time is 5. Okay. So
5.
every node will be having two part. One is when it was started and when it is ending. Okay,
Yes, sir.
something like this. Are you getting?
Okay. Yes, sir. Yes.
Who is asking?
Sir, Aditya.
So this two also will be executed because whenever we are finished at this guy, then that means u dot color is black, so we have to come back. The control will be coming back here, and then it will be executing these two statements. And then it will be coming here, so again the same thing, everything is there, blackened, so we have to execute these two statements. So it will be 6 and 7 and then 8. Okay. Maybe I can take this one. Hmm. So now, can you tell me that? So you see here, uh, you see this thing. You see this part. This part is somehow connected to each other. So, say to some extent connected. Okay, but you see this. As I told you that okay, from here I cannot go there. So this DFS control, after doing all this portion, after doing this portion, it will be again coming, the control will be again coming back here. And it will be checking which node is white. Okay. So at that time, it will be taking this guy. And you see, it was the finish time was 8. And then the initial time of this guy will be 9. Okay. And then again the DFS is going on, like that way it will be exploring. So if I am having this node structure, so this is u, v, x, and then this is y. So can you tell me, say this is the start node set. what will be the value here? What will be the first time it is explored? What will be the value? 0 or 1
So
or
1.
2 what?
So 1.
1. Okay. Then say it is going to this side. So it will be, its value will be 2. Okay. Right? Then it will be going which direction? X or Y?
Sorry, X.
X. So what will be the value?
3.
3.
3.
And then is it exhausted? X. Is there any other way we can go from X to other?
No, sir.
No, sir.
No. So what will be the value here?
Oh, 4.
4. And it will be black hand. And then the control will be coming back where? Control will be
V.
coming back where?
So V.
So we have parent pointer like this. It will be coming back here. And its value will be
5.
5. Yes. 5. 4 and then 5. And then the control will be coming back here, U. And its value will be 6. Okay. Right. And then the control will be coming. Can you tell me then after doing that, in which line the control will be coming? Here in this algorithm? In this algorithm, in which line the control will be coming back?
Sir, 6th.
So line.
Line? Line? Here or here it will be repeating on and on. Here or the control will be coming here.
So line number 5. For each vertex we have to explore now. So Y
So
has to be explored.
line number 5 it will be coming back. In that line number 5, which vertex
Y, Y.
it will be seeing that which vertex, say there is another node. So which vertex is still white? It will be say discovering that say Y is there. And what will be the initial value of this?
7.
7. 6 is the last one. So 7. And then it will be exploring this guy, right? So this is 8. And then we cannot explore any other thing. So it will be 9. And then we have to come back here. And it will be 10. Okay. Right?
Yes, sir.
So everything is done. Right now, every node is explored. And we have collected the information when it was explored and when it was ended. Okay. So in the next class, we'll see, in the next class, Thursday, I'll be taking the last class. And maybe the last class, I'll be taking, say, 1 hour at least. So join sharply on Thursday. Okay. And we'll be seeing that what is the application of this start position and end position, as the start time and end time. We'll be having one application in finding the connected component. Right. And it is having good application on topological sort also. Topological sort. Actually, this start time, finish time, then topological sort is discussed in CLRS with an example that how we dress up. Okay. Say we are first we wear shoes. We wear shoes, and then we are then we wear these socks. Okay, shoe first and then socks. So then that will be a disaster, right? So we generally wear socks first and then shoes, right? So this start time and finish time will be guiding us that which dress we have to wear first and which will be next. Okay. So that is the main idea of this topological sort. This is called event before relationship. Okay. One event, say, until and unless you are completing all the subject of first year, you cannot enter into the subjects of second year. So this is called the event before relationship. And if we are trying to maintain this relationship into a graph, then which courses we have to take first, if we want to know automatically with a programming, then the topological sort, and then the BFS will be DFS will be coming into picture. So we'll see the connected component and whether this end time, finish time, whether it is coming into picture or not. But that will be heavily coming into picture in this topological sort. Okay. Okay. So today up to this, any other question?